What we're going to be talking about today are different types of forces and how we can diagram those forces or draw a picture of those forces with something that's called a free body diagram. Hopefully, in the computer lab already, you have seen some simple examples of free body diagrams, and so you know how we would represent a force and different kinds of objects with a simple picture. But again, we're going to go through that today just as a review, and we're also going to go through some of the different types of forces that you might put on one of those diagrams and how you can label those and where you might find those in those pictures. So first, we'll start off with a very basic definition. If we are going to talk about types of forces and learn how to draw them on free body diagrams, we need to know what they are. What is a force? The simplest definition of a force is something that causes objects to accelerate. We have already talked about acceleration. We know that that's a change in velocity, meaning you're speeding up or slowing down. So a force is something that causes objects to do that. It causes objects to accelerate, either speed up or slow down. Something that causes an object to accelerate might be something as simple as a push or a pull. On an object, on a door, on a desk, hopefully not on a person, but something like a push or a pull that causes objects to change their speed is a force. There are lots of different types of forces. We are going to go through about 5 different forces today. All of the ones that we are going to go through are called contact forces. That means that the objects have to be in contact for that force to occur. There are other kinds of forces where the objects don't have to be in contact, such as a magnetic force, but we won't get to that until later in the semester. So all of the forces we're going to do today are going to be contact forces. The first kind of force that we are going to talk about is called an applied force. And an applied force is a very general term that can be used to describe a force that doesn't otherwise have a name. In a minute, we're going to go through some very specific forces that only occur in certain situations, but the applied force is more of a general force. It can be used to describe lots of different things. As a definition, the applied force is a force that is applied to an object by another object. This could be 2 cars colliding, this could be 2 people colliding, this could be a book sitting on a desk. The applied force is the force that's applied to an object by another object. And again, it's just a very general force. You can use it for a lot of different situations. The next force that we're going to talk about is called the gravitational force. We abbreviate the gravitational force usually with an F grav, or sometimes you'll just see an FG, usually a little g. FG or F grav is the gravitational force. As you might be able to guess, a definition for the gravitational force is simply the force of gravity on an object. The Earth has a force of gravity, the Moon has a force of gravity, the Sun has a force of gravity. The force of gravity on an object is called the gravitational force. Before we go on to the next type of force, we need to pause here and talk about a couple of special things about the force of gravity. One of them is a simple equation. We can find the force of gravity by taking the mass of an object, that's the m, times the acceleration due to gravity, symbolized with a lowercase g. You might remember from the Reacting to Gravity lab, where we dropped the meter sticks, that lowercase g stands for the acceleration of or due to gravity. The acceleration due to gravity. You might also remember from the Reacting to Gravity lab that the value or the number for the acceleration due to gravity was 9.8 meters per second squared. And that is on Earth. And most of the time we are going to stick to on Earth because that is what we're most familiar with. And remember, we said that the m in this equation stands for mass, the mass of the object. And because we're in science class and we always use metrics for this equation, mass needs to be in kilograms. And in case you're wondering how to take this equation and solve for each of its different parts, we can take this 3-variable equation, there's 3 different things, the f, the m, and the g, and we can put this into our algebra triangle just like we did with our speed, distance, and time equation. So in our algebra triangle, the force goes on the top, the mass and the gravity go on the bottom. And remember, how you use this is by covering the thing that you're looking for, and then what's left tells you what to do. So if you were going to find force, you would cover the F, and then mass next to gravity means multiply those two things. If you need to find mass, then you cover the M, and it's force divided by gravity. A couple more side notes about the force of gravity. In our last lesson, we learned about gravity, and we also learned that gravity is the difference between the word mass and the word weight. The force of gravity on an object on Earth is equal to the weight of the object. And remember, we talked about how weight and mass are different. Weight depends on gravity, mass doesn't. Mass is how much matter an object contains. So if you think about a person, if that person goes to the moon, you feel like you weigh less, but your mass has stayed the same. We can use this little piece of information to be able to find one more thing about different objects that we might be dealing with. If the force of gravity on an object on Earth is equal to the weight of the object, that means that weight is equal to Fg, the force of gravity. Remember, sometimes you see it written this way, F grav. Therefore, the weight of the object is also equal to the mass of the object times the acceleration due to gravity. This is the same equation we had in the box on the previous slide. I've just substituted the word weight for the force of gravity, because if those two things are the same, they must be equal. That means we can use the same equation to find them. The next kind of force we're going to talk about is F norm, or you might be able to guess that that is called the normal force. The symbol for the normal force can be F norm, or it can also sometimes be a capital F and a capital N, the normal force. The easiest way to think about what the normal force is to think about one object that's resting on another. The normal force is the support force exerted on an object which is in contact with another object. If you have two things that are in contact, for example, a book resting on a desk, the desk must be having a force or applying a force on the book to keep that book from falling to the floor. There's a force there that's supporting the book. That's the normal force. The normal force is a support force when two objects are in contact. As another example, for an object resting on a horizontal surface, the normal force is the upward force that balances the weight of the object. And we haven't really gone over how to draw a free body diagram yet, but you did see some in your computer lab activity the other day. So just as a real quick picture, if I had a table and I put a book on the table, that book has a weight. Its weight is the force of gravity, and that pulls down. And we could label that in the picture with Fg. It also then is being supported by the table. The table is applying a support force. That support gets the special name of the normal force, and that symbol is an Fn, the normal force. And that goes upward because it has to be supporting the book upwards, otherwise the book would fall to the floor. The next one we're going to talk about is the frictional force. Again, there are a couple different abbreviations for that. You can use the one at the beginning of the slide here. Or, for a little bit more shorthand, you can use a capital F and a lowercase f, the frictional force. This is the force that opposes the motion of an object. Friction is what allows anything moving along the surface of the earth to gain traction. Friction allows your tires to gain traction on the roadway. Friction allows your shoes to gain traction on the floor. That traction is the friction force, and the friction force acts in the opposite direction of the motion. In other words, it opposes the motion. And that's actually what allows you to move. If there wasn't any friction, it would be kind of like a giant ice skating rink or a giant pinball machine where you couldn't stop and everybody just kind of slid around and constantly bumped into each other. So friction is actually a pretty useful force, and it's the force that opposes the motion of an object. The last one that we're going to add to our list today is the air resistance force. And we usually use the symbol of F-air, air resistance force. The air resistance force is a special type of frictional force. It is a friction force which acts on objects as they travel through the air. So air resistance is friction. It's just a special kind of friction. Because it's a frictional force, this force of air resistance also always opposes the motion of an object. That means if you have an object that is falling down, air resistance is a force that is acting in the upwards direction. It would be trying to slow that object that is falling. Many times, this force of air resistance is ignored simply because it is too small to worry about. When we're talking about everyday objects that especially that we might deal with in class, a car rolling across the floor, a toy car, or your paper airplanes flying through the air, we usually don't talk about air resistance. We don't calculate it. It's really too small to worry about on a small scale. If you started dealing with larger things like real airplanes or hot air balloons or even trucks and cars on the highway, then it becomes a little bit more important. But for the most part, we're going to ignore air resistance. It's kind of complicated, and usually it's beyond what we need to do. There is one word that we probably should know that goes along with this idea, and that word is negligible. Negligible. Let's see if I can fit it off in the margin here so you can see it. There we go. Negligible. That means to ignore something or to neglect something. It comes from the root word neglect. So most of the time, air resistance is too small to worry about. We aren't going to tackle it. It's too complicated, and it's a little bit beyond where we need to go. All right, now let's learn how to draw some free body diagrams or review what you learned in the computer lab the other day about how to draw free body diagrams. A free body diagram is a diagram or a picture that shows the magnitude, in other words, the strength. Magnitude is the same thing as saying strength. And direction of all of the forces acting on an object. Forces are like velocity in that they have two parts. Velocity, we said, was the number of speed and the direction the object was going. Forces kind of work the same way. They also have two parts. A force, or a free body diagram of a force, has a magnitude, in other words, a strength, and again, it has a direction. It shows you which way that force is acting. Next, we'll go through some of the symbols you learned in the computer lab on how to draw a free body diagram, and we'll do a couple practice examples. First, we use the arrow symbols to show the magnitude. Again, that's the strength. And the direction of all of the forces acting on an object. The size or the length of the arrow indicates magnitude. And again, that is the strength of the force, so the longer the arrow, the stronger the force. The direction that you point the arrow is, of course, equal to the direction the force is acting. So if you have something that is being pushed to the left, then your arrow of that force would point to the left. The next thing we need to know about drawing a free body diagram is that our force arrows, or our forces, will always start at the center of the object. And there isn't really a good reason for this. This is just the way these pictures are drawn. All of your force arrows need to start from the center of your object. The next thing about drawing these pictures has to do with the amount of forces that you will need. And the number of forces you need for your picture will vary depending on the circumstances. It changes with the story problem or with the picture you're drawing. But forces always come in pairs. If there is a force to the right, there is a force to the left. If there is a force up, there is a force down. However, if the story problem you're doing says to neglect something, or it says something is negligible, that means that you don't have to draw that arrow. That force is there. Forces always come in pairs. That means you don't have to worry about drawing it. So that's the one exception to that rule. The next thing about drawing these pictures has to do with acceleration. If there's an object that's moving and it is accelerating, meaning its speed is changing, it could be speeding up, it could be slowing down. But if it's moving and it's accelerating, that means that your forces are unbalanced. One force is acting more or stronger than the other, and your arrows in your picture should be different sizes. If one force is stronger than the other, one arrow should be longer than the other, and it would be the one in the direction that it's accelerating in. So if it's speeding up to the right, the longer arrow should be to the right. One last thing before we do our examples. If you have an object traveling at constant velocity or constant speed, that means that the forces in that scenario are balanced. Forces are balanced. In other words, those forces are going to cancel each other out. If you have two equal forces in opposite directions, those forces will cancel each other. So there's two situations that might happen. One would be constant velocity. Think about like a car on cruise control. The other situation might just be that the object is sitting there. It's just stopped and it's not moving. So in those two situations, your arrows would be of equal length in opposite directions, and that means that they cancel each other out. Okay, let's do some example free body diagrams. Here's our first one. An object is accelerating to the right. I don't know what the object is, it doesn't say. So just as a generic object, let's use a rectangle. We know that our forces always start from the center of the object, so we'll put a dot in the center. And there's a pretty good chance this object is sitting on the ground, so we'll put the ground in too. We need to label the forces that we know. It tells us in the question or in the problem that this object is accelerating to the right. That means that there must be a force to the right, and it should be a pretty long one if we're speeding up. If there's a force to the right, then there also has to be a force to the left. But it's got to be smaller or shorter if the object is accelerating to the right. Let's see if we can think about what these might be. The one to the left, the white one, is the one that is in the opposite direction of the motion. So if it's opposing the motion, then the white one must be the friction force. In this particular problem, it doesn't tell us what that motion is being caused by. We don't know. So the force to the right is probably just our general force or our all-purpose force, and that was force applied. For force applied, you can use the FAPP that you saw earlier in the notes. If you want to be a little shorter, you can use capital F, capital A. That stands for force applied. And one little note I'm going to put off to the side here. Remember we said that the force applied has to be greater than or bigger than the friction force because the object is accelerating to the right. So when you're drawing these pictures on a test or a quiz, if you're afraid that I won't know which arrow is supposed to be longer, you could always write me a little note off to the side to say this one is supposed to be longer than the other one. Okay, even though we've covered everything that was stated in the question, believe it or not, there's two more forces that exist in this picture that we have to draw. One of them is the force that is always present, all the time, because you live on Earth. That's the force of gravity, and the force of gravity points down. Again, symbols for that, you can use F-grav or you can use Fg. And if there is a force pointing down, then there also has to be a force pointing up. But this object isn't moving up or down. It's only moving to the right. It's not moving up or down. So that means that my up arrow and my down arrow should be the same length. So I'm going to try to draw them about the same size. If gravity is pulling down, and this object is not falling into the center of the Earth, there must be something supporting that object. In this case, it looks like the ground, but that force has a special name. The support force, remember, was the force normal, Fn, force normal. And in this case, because our object is not moving either up or down, gravity should be equal to normal. Okay, next one. Example 2 says a falling object. Sounds pretty simple. Again, I don't know what that object is. It doesn't tell me, so I'm just going to use a box. We know that all of our forces need to start in the center of our object, so I'll start with a dot as my center, so I know where my arrows start. It tells me this object is falling, so I'll assume that it's falling through the sky, and maybe we'll add some clouds over here. So we have a box falling through the sky. The first force that we need to draw is, of course, the force that's making this object fall. That force is the force of gravity that is pulling that object towards the Earth. And if that object is moving towards the Earth, accelerating towards the Earth, we know that it accelerates because of our meter stick lab that we did. That force of gravity arrow should be pretty long. And if there's a force of gravity going down, there must be another force going up. It should be a shorter one because the object's falling down and accelerating down. And this one is that special kind of friction force known as the air resistance force, or force air, F-air. You could also put just the plain old friction force here. That would also be correct, because remember that the air resistance force is a friction force. And again, if you were doing this on a test or a quiz and you were concerned that I wouldn't know which arrow was supposed to be longer, you could write me a note. The force of gravity is supposed to be greater than the force of air resistance. And that picture's done. We don't have any side-to-side forces on here because the object is simply falling straight down. Okay, last one. An object moving to the left at a constant velocity. Notice that constant velocity is in italics. That must mean it's important. Again, I don't know what our object is, so I'm just going to start with a box. We know that all of our forces start in the center, so we'll add a dot. We assume that this object is sitting on the ground because it doesn't tell us otherwise. And now we're ready to start putting in our forces. If this object is moving to the left, there must be a force to the left. And it doesn't tell us what that is, so we can use our general force, which is force applied. There's some force being applied to move this object to the left. If there's a force to the left, there also must be a force to the right. It's moving to the left, so the one to the right should be the force that opposes motion. And the force that opposes motion is the friction force. Notice the length of those two things. If we are at constant velocity, that means that my forces are balanced. And if my forces are balanced, they are equal. So the force applied should be equal to the force of friction. And again, if you weren't sure on a test or a quiz that I would know that from your picture, you could write me a little note. But we're not done yet, because this box is sitting on the ground. And if it's sitting on the ground, there must be a force pulling it downward. Hopefully we know that that is the force of gravity, or Fg. And if there's a force that's pulling it downward and it's not sinking into the center of the Earth, there also needs to be a force supporting it. That'd be the ground in this case, but that force is called the normal force, or Fn. The object is not moving either up or down and is not accelerating either up or down, so that tells me that those two forces are also balanced and must be equal in magnitude or strength. All right, we are all finished for today. Hopefully you've learned some special forces and you know how to draw a free body diagram.